Today's topic is differences between ideal and real gases. Compressibility factor. What is compressibility factor Z? And Vaderwaal equation. How the scientist Vaderwaal corrected the ideal gas volume and pressure. Volume correction and pressure correction. See one by one. First of all, we'll see about the differences between ideal gas and real gas. What is ideal gas and what is real gas? The gas which obeys ideal gas equation, such type of gas is known as ideal gas. Which obeys ideal gas equation means PV is equal to nRT. The gas which does not obeys ideal gas equation, such type of gases are known as real gases. These real gases obeys Vaderwaal equation. This is known as Vaderwaal equation. P naught plus A by V square into V minus B is equal to RT. No definite volume. Ideal gas point is no definite volume, but real gas is having volume. No intermolecular attractions are present in ideal gas, but intermolecular attractions are present in real gas. Ideal gas molecular collisions are known as elastic collisions, but real gas molecular collisions are non-elastic collisions. And real gas does not really exist in the environment and is a hypothetical gas. All these equations is all hypothetical, but it is really exist in the environment. We have many gases are there in the environment. Ideal gas is applicable at high pressure, but real gas is applicable. The pressure is less when compared to ideal gas. Ideal gas exists independently, but real gas they interact with other gaseous molecules. So these are the differences. Now we are seeing about the compressibility factor Z. What is compressibility factor? And through this, how we can separate the ideal gases and non-ideal gases, it means real gases. Based upon compressibility factor, we can decide which is real gas and which is ideal gas. Real and ideal gases can be compressed at various pressures and various temperatures by noting the extent to which the value of PV by RT deviates from Z is equal to PV by RT. The compressibility factor is represented by Z. Z is equal to PV by RT, the product of pressure and volume ratio with ideal gas constant absolute temperature. The quantity is given by the symbol Z and the name is compressibility factor. Based upon compressibility factor, when Z is less than 1, this implies that the gas is more compressible. When Z is greater than 1, this means that gas is less compressible. When Z is equal to 1, the gas is ideal. So when Z is equal to less than 1 or greater than 1, these two are indicates real gases. These two are real gases. When Z is equal to 1 value, when you get that is ideal gas. These real gases, when in that either greater than 1 or less than 1. So when greater than 1, that indicates less compressible. When less than 1, that indicates more compressible. See here the graphical representation. X axis a pressure, left hand side in y axis we have taken the product of P and V. PV versus P, it indicates Boyle's law. You'll get a graph straight line from left to right. See here, this is the graph between PV versus P. Already we know that the product of pressure and V versus pressure, this graph will come. So this graph for ideal gas only, all Boyle's law, Charles law, Avogadro's law all will applicable for ideal gas only. So for this ideal gas, always Z value should be 1. Z means what? Compressibility factor. See here, Z value is 1. When Z value is greater means above the line, that is real gas. A Z value is less than 1, that also real gas which will come under this. So this is real gas and ideal gas graphical representation. So here this is ideal gas. When above whatever the curves will come which comes under real gas and below also real gas. We'll see one by one. See here helium is the real gas. When you observe the graph between PV versus P, the real gas graph should be like this. It is increasing, positive deviation above this line. So above the Z value, above the 1. Hydrogen also real gas. This graph also when you observe, this is looking like this. Then one more real gas I am taking, that is carbon dioxide gas. Carbon dioxide gas, how it will come? First it deviates from ideal gas. Deviates means instead of straight line, it is coming down. This is called negative deviation. Why? Because 1 Z value will come minus. So less than 1, it is negative deviation. And afterwards again, it is moving towards up direction after that positive deviation. So this is about CO2. And one more gas I am taking, methane gas. Methane gas also when you observe the graphical representation, first it is coming down, negative deviation, and then touched at this here and then positive deviation. It means value will be positive. Above the 1, positive value. Below the 1 is negative value. Negative deviation, positive deviation. So, a real gas's graphical representation gas to gas will be different. But in ideal gas, it will be straight. The compressibility factor Z is equal to 1. So, at high pressure, see here, at high pressure, this all gases will show like this. At high pressure. And low pressure, so these are the compressibility factor values 1, 1.2, 1.4, 1.6, 1.8. It means Z is Z value 1 when greater values are there here 1.2, 1.4. Then Z value increases, real gas character increases. Z value decreases also, real gas character increases. See here, either below the curves or above the curves, both will indicate a real gas. Both will indicate real gases. So the below the curves will form at low pressure, and above the curves, whatever you are seeing, the curves will form at high pressure. Here, Z value is less than 1, 0.8 or 0.6, 0.4. So that is a real gas. And Z value is above the 1. This also indicates real gas. When Z is equal to 1, that is ideal gas. Based upon compressibility factor, we can decide which is the real gas and which is ideal gas. When you observe one more graphical representation, same Boyle's law. We have studied about Boyle's law. P is inversely proportional to 1 by V. So when you take a graph between P versus V, the graph will come like this. So when pressure is moving from left to right, bottom to top, and volume increases from left to right. At particular this volume, this is the pressure. It means at higher volume, pressure will be low. At high pressure, this is the high pressure. At high pressure, the volume will be less. It means pressure increases, volume decreases. Pressure decreases, volume increases. This is we studied in Boyle's law. V is inversely proportional to P or P is inversely proportional to V. See here, this is about a ideal gas graph. Observe here, this is the ideal gas graph. It is moving down like this. When you draw the real gas, same pressure versus volume, the graph will be coming like this. The graph will be coming like this. This is also pressure increases, volume decreases, volume increases, pressure decreases. When you observe these two graphs at particular point they are connecting with each other. This point is known as having, this is the volume, at this particular point this is the pressure. Yes, at low pressure or high pressure, this is the high pressure. At high pressure, ideal gas is different and real gas is different. But low pressure, when pressure decreases, at low pressure, the real gas becomes what? Ideal gas. Very important. At low pressure, high temperature, real gas become ideal gas. Very important point. For that reason only I am showing you, always the real gases act as an ideal gas at low pressure and high temperature. Now we are discussing about Vaderwaal's equation of states of real gases. Vaderwaal equation is obeyed by real gases only. Ideal gas equation obeys ideal gas. Vaderwaal equation obeys real gases. Wide range of T and P, and hence this equation is called as equation state for real gases. I am showing you Vaderwaal equation. This is the Vaderwaal equation. This is for 1 mole of gas. P plus A by V square into V minus B is equal to RT for 1 mole. For n moles, you can write nRT. This is like this now. PV is equal to nRT. We know nRT. This is same nRT. Instead of P, what I have written this one. P plus AN square by V square. P plus AN square by V square. Instead of V, what I have written? V minus NB. It means the P is corrected as this, like this. P plus AN square by V square. V means volume corrected as V minus NB. Real gases obeys this equation. Ideal gases obeys this equation. So scientist Vaderwaal corrected the PV n is equal to nRT. This is applicable for only ideal gases, but this is the correct gaseous equation, real gas equation. What is that? P plus AN square by V square into V minus NB is equal to nRT. So P added by something. This one. What is that something here? AN square by V square. The V minus NB. Here A and B are known as Vaderwaal's constant. How the scientist Vaderwaal corrected the pressure and as well as volume, we are going to see in the next slide. Where A and B are the constant characteristics of gas, this equation can be derived by the considering a real gas and converting it to an ideal gas. Vaderwaal pointed out that in the case of real gases, molecules do not have a volume and also exert intermolecular attraction, especially when the pressure is high and temperature is low. He modified the ideal gas equation by making necessary volume and pressure corrections and presented it as a Vaderwaal equation. So after correcting, you got this equation. How he corrected, I am explaining. First, volume correction. Actually, whatever the gas equation they proposed, ideal gas volume is equal to real gas volume. When PV is equal to nRT, we have learned that PV is equal to nRT. This is applicable for what? Ideal gas. The same equation also should applicable for PV is equal to nRT for real gas also. But when you observe that in the previous graphs, entirely different real gas and ideal gas. That is the reason here whatever the volume is there, PV, in this volume, for example 10 liters, in real gas case also will get 10 liters. But not like that. But real gas volume will be not equal to, it was somewhat extra volume is coming. When you calculate ideal gas volume 10 in this equation, originally when you see that gas volume will be somewhat extra is coming. For example, 15 or 20 liters like that. So that is the reason correction is required. So hence, ideal gas volume is not at all equal to the real gas. Ideal gas volume is not at all equal to the real gas. For example, this is the gas. This is the gas is there. This gaseous volume is ideal gas. So whatever the gas is there, for example hydrogen gas, its volume is 10 liters. Okay. But originally, as per this 10 liter, as per PV is equal to nRT formula, this volume is 10 liters. But actually when you observe H2, we are getting 15 liters. We are getting 15 liters. So that what happened? So both are not equal. That is the reason I am giving ideal gas volume is not equal to the real gas volume. How we are going to correct it? See here. So ideal gas volume is less and real gas volume is high. What I said? Ideal gas volume is 10. I told you 10 liters. 10 liters. Real gas volume originally when you correct what is coming? 15 liters is coming. That is the reason real gas volume always higher than ideal gas. So ideal gas is less than real gas. Vaderwaal assumed that the gaseous molecules are rigid sphere with definite volume. If the observed volume of a gas, observed volume means real gas volume, then its effective volume will be V minus B, where B is the volume occupied by the 1 mole of gas molecules, referred as excluded volume. So that V ideal is equal to V real minus B. See here, real gas and ideal gas I told you. For example, in ideal gas case, you are getting 10 liters volume, 10 liter volume. But in real gas, this is coming as 10 liters plus 5 liters extra is coming. Total its volume is 15 liters. So this is the ideal gas volume is 10 liters. So what will happen? Real gas is 15. 15 is real gas. Volume is 15. From this 15, when you remove B means what? This one. Extra volume. This extra volume is known as excluded volume, which is represented with B. When you remove this B, now ideal gas volume, you will get how much value? 10 liters. And ideal volume also how much? 10 liters. Now the equation will be satisfied. 10 liters is equal 10 liters. When it will happen? When you want to remove B. When you remove B from real gas, then ideal gas is equal to the real gas volume. So this B is known as excluded volume. So how we can remove, sir, means as per the kinetic molecular theory of gases, we have a equation is there, PV is equal to nRT. PV is equal to nRT for 1 mole means PV is equal to 1 RT. PV is equal to nRT. Here when you keep 1, you will get PV is equal to RT. Here V means, instead of V, what you have to substitute? V minus B. Why we are substituting V minus B? As per the kinetic molecular theory, the molecules present in the gaseous mixture, the single molecule volume is negligible. As per kinetic molecular theory of gases, when you compare entire whole gas volume with a single molecule volume is negligible as per ideal gas. But Vaderwaal, what he said is, no, not at all. We should not neglect this molecule. So this molecular volume also considerable. This molecule volume also considerable. That is the reason only we are getting extra volume. In ideal gas, we are taking 10 liters. Why we are getting 15 liters in real gas case means, in ideal gas, you are not consider the single molecule volume. But that should also we have to consider. When you consider it, so then only the ideal gas volume will be corrected. So that is the reason this volume, whatever the molecules are there, this volume is represented with BMA. B means excluded volume, extra volume. This also you have to add excluded volume. So for n moles of gas, the effective volume will be V minus NB. One molecule V minus B for one molecule. More molecules are there, you have to write V minus NB. Means extra volume. You have to remove the extra volume. The ideal gas equation PV is equal to RT is now written as how? P into V minus B is equal to RT. Right? Instead of V, what we have to write? V minus B. Because the V volume, actual volume is 15 liters. That 15 liters you have to remove 5. Then you will get 10 liters. So that P, instead of V, you have to write V minus B. In this way, scientist Vaderwaal corrected the volume. Instead of PV, V, instead of V, he corrected as V minus B. B means excluded volume, extra volume. Okay. The excluded volume B is actually 4 times the actual volume of gas molecules. So B is equal to 4 Vm. 4 times the actual volume of the heavier. B is equal to, wherever B will come, you have to substitute 4 Vm. One molecule volume is 4 times. So ideal is equal to V real minus 4 Vm. Correct? Instead of V, what we have to substitute? V minus 4V. V minus 4B. V minus B means what? V minus B. B is the excluded volume, extra volume. Instead of B, what you have to write? 4V. Instead of B, what you have to write? 4V. B is equal to effective volume of the molecules per mole of gas. This is about the volume correction. Now we see about prove how B is equal to 4V. 4 times B. Why sir? Why it is 4 times heavier? We'll see the derivation. Generally, when you take the two molecules, this molecule radius is R1. So this is from here to here. For example, this is R1 and here to here this is R2. This case is two molecules. This is molecule A, for example, molecule B. So in this case, 4 by 3 pi r cube volume formula. For anything, volume formula is 4 by 3 pi r cube for this case, sphere. So R plus R, can I write 2R? V pair, this is about single molecule, is 4 by 3 pi r cube. I am taking entire whole V pair. When you take 4 by 3 pi r cube, 2R. Instead of R, I have substituted 2R. So instead of R, I have substituted 2R cube because it is a pair. V pair is equal 4 by 3 pi. So 2 into 2 into 2, so that 8R cube. This we can modify like this. This 8 comes to here. V pair is equal to 8 into 4 by 3 pi r cube. So for one molecule, we have done this pair, but I want only one molecule. One molecule means you have to divide with 2. When you divide with 2 this equation, what will come? 2 4 is 8 will come. So V1 molecule is equal 4 into 4 by 3 pi r cube. This 4 by 3 pi r cube means what ma? Vm. Volume of the molecule. Volume of the molecule. So volume of the molecule you have derived. V1 molecule is equal to 4 Vm. Instead of B is equal to 4 Vm. We have proved. Proved B is equal to 4 Vm. It means one molecule extra volume is equal to B is nothing but 4 Vm. So as per the Vaderwaal equation, instead of B, you can substitute it 4 Vm. Next one is pressure correction. So we have an ideal gas equation, that is PV is equal to nRT. PV is equal to nRT, where V is corrected. How we corrected? P into this V minus B is equal to nRT, right? Instead of B also we can write V minus 4 Vm is equal to nRT. So pressure, volume we have corrected. Now we are going to correct the pressure. How we can correct the pressure? See here. P ideal is not equal to real gas. Same way, whatever the pressure we have taken for a gas, same gas I have taken. Each and every gas have some pressure. So that pressure is P ideal pressure. And when you observe really what is the pressure means, the P ideal pressure is high here. Here this pressure is 15 atma is coming. When you observe really, the real gas atmosphere is 10 only coming. The real gas pressure is 10 atma is coming. It means the variation is there. That is the reason P ideal is does not equal to P real. P ideal gas is always higher than the P real gas pressure. So what we have to do? Ideal gas pressure is 15. Ideal gas pressure is 15 Pi, and real gas pressure is 10 only, 10 atmospheres. This is P real. We have to equal the ideal means you have to remove what here? Here you have to remove 5 atmospheres. Then 15 minus 5 is equal to 10. This 15 is what? P ideal. Minus you have to remove something here. I am indicating with the letter A. Minus up, then you will get the pressure correction simply. So now we'll see one by one. At ordinary pressure, the gas molecules are far apart, and so the intermolecular force between them is nearly zero. But on increasing the pressure, the molecules come closer and begin into the attract one another. Molecules in the interior of the gas at attract from all sides becomes ineffective due to cancellation of equal and opposite forces. But the molecules which are near with walls of the vessel experience only an inward pull due to balanced attractive force, which makes the molecules collides against the walls with a small momentum. Thus, the absorbed pressure is less than the ideal pressure. Thus, the pressure correction P is done. P ideal is equal to P absorbed plus P prime. P prime means extra pressure, decreased pressure. So, P ideal is equal to P real plus P prime. Now, I am explaining all this theory, pressure correction, how we have done. No force of attraction, P ideal is not equal to P real. Force of attraction and pressure correction, how we are doing? As per the ideal gas equation, as per the kinetic molecular of theory, the intermolecular attractions are negligible, they told. But Vaderwaal is considering the intermolecular attraction. That is the reason only pressure is getting high. See here, this molecule attracts A and B, different types of molecules. For your understanding, I have taken this A molecule attracts B, B molecule attracts A. And here the B molecule is attracting, here also the B molecule is attracting on A. So here the attraction force are balancing. And one more point we studied in kinetic molecular theory of gases, when collides with each other, molecule collide with each other, and these molecules collides with the container also. This is the walls of the container. During this, pressure will be increases. But when you observe here, in case of this molecule, this B here, A is there, this side there is no other molecule is there. That is the reason the pressure is not balancing. The intermolecular attraction is not balancing. But here the intermolecular attraction forces are balancing. But in this molecule, the A is attracted by B. This is inward pull attraction. Attract itward towards B side. Inward pull attraction. Inward pull attraction. Inward pull attraction. That is the reason this A will go and bombarded slowly with the walls of the container. Hence, pressure will be low. Pressure will be low. So here they can balance the intermolecular attraction forces. So that is the reason the ideal gas pressure is not equal to the real gas. We'll see one by one. So this is molecular attractions are balanced. This is inward pull, A type of attraction due to B. Due to B, A is inward pulling. Pi is equal to P naught plus P prime. P ideal P ideal gas is what I told, 15 atmosphere I told you. Just assuming for your understanding, 15 atmospheres ATM. But generally, ideal gas pressure is how much ma? 10 atmospheres only. What is extra, Nana? That extra pressure I am indicating 5 with P prime. This is P naught, ideal gas pressure. This is ideal gas pressure. This is the real gas pressure. This is P naught is observed pressure. Observed pressure means real gas. Pu naught means real gas. Or PR you can keep it. So real gas pressure is 10, but ideal gas pressure is 15. But why the variation is coming means here the weakly attraction forces are there. These molecules exerts pressure happily, but because of inward pulling, this A molecule is attracted by this B, this A molecule is attracted by this B, and this A molecule attracted by this another B. Because of this, it is slowly bombarded with the container. Hence, the pressure will be less. Instead of 15 atmospheres, pressure will be less. So, ideal gas is 15. How much less means? This much less. Whatever the less atmosphere, when you add to the real gas, you will get the ideal gas pressure. So that's the reason the decreased pressure we are adding to the real gas. Then only ideal gas pressure and as well as real gas pressure should be equal. That's the reason what is the extra pressure is decreased. That decreased pressure we are adding to the real gas. So real gas pressure is 10. How much is decreased? Due to the inward pull attractions, 10 atmospheres of pressure is decreasing. That we are indicating with P naught. Okay. P naught is equal to amount of pressure which is decreased due to the attractive forces. P naught is equal to, we have formula A by V square. How the A by V square will come? We will derive it. Instead of P prime, what you have to substitute ma? A by V square. So then you will get a new equation. Pi, ideal gas pressure, is equal to real gas pressure, it means absorbed pressure, plus decreased pressure, that is P prime. How we can write this equation? Pi is equal to P real gas pressure plus A by V square. Instead of P prime, we have to substitute A by V square, A by V square. So PV is equal to nRT equation is corrected in this way. So PV is equal to RT. In case of N is equal to 1, PV is equal to RT. This is the ideal gas equation. Now this ideal gas equation is corrected by the Vaderwaal in this way: P naught plus A by V square. P naught plus A by V square. Instead of P, you have to write this one. P naught plus A by V square. Already V we have corrected. V means V minus B is equal to RT. Here B means extra volume, excluded volume. A means what ma? The amount of the pressure which is decreased due to the attractive, decreased pressure. So these two are called as a Vaderwaal's constants. For 1 mole, then finally you will get the equation P naught plus A by V square, V minus B is equal to nRT for n moles. This is called as Vaderwaal equation for non-ideal or real gases. PV is equal to nRT is modified by the Vaderwaal like this: P naught plus AV square, A by V square into V minus B is equal to nRT. Prove it. I told you P prime is equal to A by V square. How we can substitute means Ca and CEB, two molecules are there, intermolecular attractions here. This is one molecule and this is one molecule. The intermolecular attraction A and B, we have one attraction force is there. This is directly proportional to the pressure. When pressure increases, intermolecular attraction force increases. When pressure decreases, the distance will be increased. So that's the reason pressure is directly proportional to the concentration. It means the intermolecular attraction. So this we can write in this way. We know that we have a formula: concentration is equal to moles by volume. So instead of C, you can substitute P prime is directly proportional to here one C is there N by V into N by V in case of two this is a one molecule, this is one molecule. P prime is directly proportional to N into N, N square, V into V, V square, N square by V square. P prime is equal to A N square by V square. A is constant and N is equal to 1. When you substitute, you will get the answer P prime is equal to A by V square. So, whatever the decreased pressure, instead of the decreased pressure, we can represent it with P prime. So, this P prime is substituted by A by V square. Yes, after necessary corrections, you got it. The van der Waal equation is this one. After correcting pressure and volume, P plus A by V square into V minus B is equal to RT for 1 mole. For N mole, P plus A N square. Observe here, A N square. P plus A N square by V square into V minus NB. Because N number of molecules is equal to nRT for N moles of gases. This is about van der Waal equation after correcting the pressure and volume. Van der Waal equation is obeyed by real gases over a wide range of temperature and pressure, and hence this equation is called as equation state of real gases. The constants of A and B, we are discussing about A and B, some important points regarding this. One by one. Van der Waal constant for attraction A and volume B are characteristics for a given as gas as some silent features of A and B are number 1. For a given gas, the van der Waals constant of attraction A is always greater than van der Waals constant of volume B. The numerical value of A and B are, this is the order 10 to 10 to the power of minus 2 and 10 to the power of minus 2 to 10 to the power of minus 4 respectively, A and B values. A and B are van der Waals parameters which are empirical parameters and depends on the nature of the gas and independent of temperature. Significance of A and B. A higher is the value of A for a given gas. Easier is a liquefaction. Example, NH3, SO2 and hydrogen sulfide and carbon dioxide have high value of A than permanent gases such as N2, O2, H2 and helium. Hence, the value of A is said to be a measure of intermolecular force of attraction. B, the value B gives an idea about the effective size of gas molecules. Greater the value of B, larger the size and smaller is compressible volume. Constant volume of B for over a long range of temperature and pressure indicates the molecules are incompressible. Units for van der Waals constant A and B are expressed in terms of the units of P and V. P is equal to A n square by V square, then A is equal to P prime V square by n square is equal to atma liter square per mole square. Units of A is equal to atmosphere liter square and mole per mole square. SI units Newton meter for and mole to the power of minus 2. So these are the units. In this way we can measure the A and B. Van der Waal equation at different pressures. Different pressures, how we can express the van der Waal equation. At low pressure, V is large and B is negligible in compression with V. The van der Waals equation is P plus A by V square into V is equal to RT, or PV is equal to RT into minus A by V. At extremely low pressure, V becomes so large that the both B and A by V square becomes negligible and the van der Waals equation reduced to PV is equal to RT. All high pressures A by V square may be neglected in compression with P. The van der Waals equation we can write at this situation P into V minus B is equal to RT, or PV is equal to RT plus PB. Van der Waal equation and different temperatures we have observed. At high temperature, V is very large, so both factors become negligible. Hence, van der Waals equation becomes PV is equal to RT. At low temperature, both P and V are small and both corrections are appreciable. Hence, the van der Waal equation is P plus A by V square into V minus B is equal to RT. Drawback. Drawbacks. The values of A and B do not remain constant over entire range of temperature and pressure. Deviations are observed in the equation at very high pressure or very low temperature. The value remains constant only over a specific range of temperature and pressure. Therefore, the equation is valid over a specific range of temperature and pressure only. This is the drawback for this van der Waals equation. Okay, students, I am going to stop at this here.